Well, we're not going to finish chapter 7. We'll get about halfway through that section. So 7.5. Solving trig equations. So we've done this already before. We did play with some equations. So let's make it official. So you'll see two types of equations. One, when you solve on interval from 0 to 2 pi, or find all solutions. So depending on the problem, you'll know what you're looking for. So we've done that. So from 0 to 2 pi, usually use a unit circle or whatever. Find all solutions, that's when you introduce the period of the function. And we spent some time on that already, so let's review this. You might have even done a homework on this, but so a few examples. Let's say I start with an equation. So solve on the interval from 0 to 2 pi. And let's say the equation is 2 cosine x equals -1. And your book does this. It's probably better if we don't include 2 pi, because usually 0 and 2 pi give you the same answer. So let's include one and not include the other. But the way we solve this equation, we first algebraically solve for the trigonometric function. So we want to get cosine by itself. So divide both sides by 2. So cosine x equals -1/2. So then you can use the unit circle. So when is the x value on the unit circle equals -1/2? So somewhere here. Right, that's the point that I want. So what is the angle measure? What? Well, this would be 60. So then what's that? 120 or 2 pi over 3, right? So then x equals is that the only solution? No. What else? Where else x equals -1/2? Yeah, if I go straight down, here's another solution. The y value doesn't matter since we're solving for the cosine. So what is this going to be? No, because that's still 60. 240, but in terms of in radians? So again, it's pi over, it's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, right? So it's 4 pi over 3. So those are the two solutions on the interval from 0 to 2 pi. If the question was find all real solutions to this equation, you'll have to go plus 2 pi k plus 2 pi k to account for the period of cosine, right? We've done this. This is very fresh in my memory. I don't know about yours. What? Why are you smiling? You don't remember? All right, let's try this one. Find all solutions. And the equation is 4 sine squared x equals 1. So what do you want to do first? Okay, divide by 4. So you have sine squared x equals 1/4 square root. So what do you need to do if you take the square root? What is sine x equals to? One half. What else? What do you need to remember when you take square root of both sides? Plus or minus. Don't forget that, because you lose half of the solution. So then, okay, when the sine equals 1/2, or negative 1/2, so again, you refer to the unit circle. So now it's the y value that equals to 1/2. So here's that other point. But then also you have negative 1/2. So this is pi over 6, right? What about this one? What's the second angular value? Well, again, it's just use the symmetry. These are all going to be pi over 6s. So if the whole thing is pi, so what is the one right before it? 5 pi over 6. And this would be 7 pi over 6. Right? And that would be 2 pi take away pi over 6. So that's 11 pi over 6. Right? Just use the symmetry of the unit circle. So we have 4 solutions. Right? So let's list them. So we have pi over 6 plus 2 pi k. Then we have 5 pi over 6 plus 2 pi k. And then we have 7 pi over 6 plus 2 pi k. Then we have 11 pi over 6 plus 2 pi k. Right? That's what it means to find all solutions. Is that right? Are you with me on this? See? Well, because because we're looking for the y values that are equal to 1/2. So they're, yeah, and then I have the, yeah. Well, there are infinitely many solutions, but there are 4 points. Now we can condense this solution, because if you think about this, the difference between pi over 6 and 7 pi over 6 is exactly pi. Right? So I can actually, instead of saying pi over 6 plus 2 pi k, and 7 pi over 6 plus 2 pi k, I can just say, well, it's just pi over 6 plus pi plus pi plus pi. So we'll just keep circling. I can actually combine these two solutions into just saying pi over 6 plus pi k. Because the difference between those 2 points is exactly 180 degrees, or pi. Same thing with 5 pi over 6 and 11 pi over 6. The difference between 5 pi and 11 pi is just one single pi. So I can combine these two solutions into just saying 5 pi over 6 plus pi k. So I can make my solution smaller, because there is redundancy in my original statement. How's that? If the question was just find all solutions on the interval from 0 to 2 pi, you would have to list all 4. You'll go pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Those are 4 solutions on the interval from 0 to 2 pi. But if we go to the entire number line, then you can make it more condensed. Well, because again, the distance between 5 pi over 6 and 11 pi over 6 is just exactly 1 pi, right? The distance between this point and that point. So the rotation is exactly pi. So instead of just going 2 pi around 5 pi over 6 and going 2 pi around 11 pi over 6, I can just jump by a single pi between those two. What? No. I didn't get 5 pi. I got 5 pi over 6. Yeah. Well, what is 5 pi over 6 plus pi? What does that equal to? No. Yeah, you do. Well, what is 5 6 plus 1? What does that equal to? Well, what is that as an improper fraction? Well, how come you don't know that? Because we're talking about, I mean, we're never going to find a common ground. What is this equal to? It's 11 over 6. It's a simple fraction. So the distance between 5 pi over 6 and 11 pi over 6 is 1 pi. Right? Yeah. So that's what that says. If you go from 5 pi over 6, you add pi, you get to 11 pi over 6. You add pi again, you'll get back to 5 pi over 6. You'll keep circling. If you do not know how to add fraction, there's nothing I can teach you in this class. That's not funny. It's very sad. Makes me sad. On the inside, know your fractions. Know how to add fractions. Okay. Now, well, let's try a few similar ones. What if we try cosecant squared minus 4 equals 0? And let's just do on the interval from 0 to 2 pi. So cosecant squared minus 4 equals 0. So how do you want to go about solving this one? Add 4. Square root. If you do the square root, what do you need? Yeah, plus or minus 2. Okay. Now, it's always hard for us to think in terms of cosecants and secants and cotangents. It's easier for us to think in terms of sines and cosines and tangents. So can we convert this equation in terms of sines, cosines, in terms of the friendlier trig functions? How would you do that? What? Yeah, so it's cosecant. If you flip it, it becomes sine, but then you have to flip the other side. So it's equivalent to saying sine x equals plus or minus 1/2. Right? So you just take the reciprocal of both sides, so you cosecant turns into sine. Now it's easier for us to think about this problem. Actually, it becomes exactly the same as the one we just did. Right? We just solved sine x equals plus or minus 1/2. That's what it came down to. Now, since the question was find all solutions from 0 to 2 pi, so after everything we just done, what are the solutions to this equation? Pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. So I need to list all 4 because that's all I need, right? It's just all the solutions from the interval from 0 to 2 pi. If the question was in degrees, if the question was find solutions between 0 degrees and 360 degrees, then you would say you have 30 degrees, right? Then that's 150. Then this is 210. And the last one is 330 degrees, right? So again, you can either convert them to degrees or just, again, using the unit circle. You get the same results. How is that? Is that okay? Okay. Well, let's play with some double angles. So let's just go from 0 to 2 pi. And the equation is 2 tangent of 2x equals, no, let's do 3 tangent of 2x equals negative 3. So what the first thing you want to do? Yeah, divide by 3. So 3 cancels on the left, so we have tangent of 2x equals negative 1, right? Now don't mind that 2x first. We don't go into like double angle formulas or things like that. Ignore the 2x for now, okay? Just think about this. When does tangent equals negative 1? Tangent of what equals negative 1? So that means sine and what? No. Sine and cosine have to be the same of opposite signs. So it's something has to do with the 45-degree angles. If you think about the points on the unit circle where sine and cosine are close, you have this one, you have this one, you have this one, and you have this one. Right? So when does tangent equals negative 1? Right, so this is the point where the tangent is negative 1 because it's a sine over cosine. It's y over x. Right, so that's negative 1 and that's negative 1. Right? So this is what? This is 3 pi over 4. And this one is, yeah, this is 7 pi over 4. Yeah. Okay? So think about this. So right now, that means that 2x, if 2x equals 3 pi over 4, then we're happy, right? So that means 2x has to equal 3 pi over 4, or 2x has to equal 7 pi over 4. Right? Because then the inside you get tangent of 3 pi over 4, that's -1. Tangent of 7 pi over 4, that's -1. So if 2x equals 3 pi over 4, what is x? Which is? Yep. So then x equals 3 pi over 8, or x equals 7 pi over 8. Right? Are you okay how we got these two? We totally ignore all the junk on the inside. We just say, well, everything on the inside has to equal 3 pi over 4, or everything on the inside has to equal 7 pi over 4. And then you solve for your variables, okay? All right. Now, since the question was find all solutions of the interval from 0 to 2 pi, are we done? We got, think about where those points are. 3 pi over 8, it's somewhere where? It's in the first quadrant. And 7 pi over 8, that's in the second quadrant. I mean, are there going to be any more solutions in the third and the fourth quadrant? How'd you get that? You added 8? I don't know. Why did you add pi?
Well, like 3 pi over 8 plus pi
Yeah.
is 11 pi over 8.
But why are you adding pi? Well, let's
Because we have to get to the
yeah, but why is it? Well, how do you know it's going to give you the same value? Well, that's not good. Huh? Well, he's right for all the wrong reasons, but he's, yeah.
We're going through the interval 0 to 2 pi.
Yeah.
So, same values in the
Well, you cannot assume that. But I mean, you kind of on the right track, but you have to convince me. I'm not whole certain about adding pi. What? Well, what is the period of this function? Because I always have to go back to that. I mean, that'll help us here. I mean, we found these two solutions. But what is the period of this function? Yeah, what's the period of a tangent function? Pi. Okay, so period. But this is not a tangent function. This is tangent of 2x. Right? So what's the period of tangent of 2x? Pi over 2. So, and if you notice, if I take 3 pi and I add pi over 2, I'll get that. If I add pi over 2 to this, I'll get my, yeah. So then x equals 7 pi over 8 plus pi over 2. So that's 11 pi over 2. I'm sorry, 11 pi over 8. And then I take that and add another pi over 2. So I'll get my 15 pi over 2. So you were right as far as the points go, but for kind of the wrong reasons, you have to be a little careful. So the reason why we're adding pi over 2 is because that's the period of tangent of 2x. Okay? So, but the distance between any of those points is just pi over 2. Right? 3 pi over 8 plus pi over 2 plus pi over 2 plus pi over 2. If the question was find all solutions, you would go just 3 pi over 8 plus pi over 2k, because then it's just multiples of pi over 2. How is that? Does that make sense? There's another way to do this problem. It's kind of a backward way. In the body of the problem, it said, find the solutions on this, right? On the integral from 0 to 2 pi. So that means x is between 0 and 2 pi. Okay, so your solution, your value has to belong to that interval. And this is what we have. All our solutions that we just found belong to this interval. Is that okay? So, but then let me ask you this. The argument inside of this function is 2x. So if x is between 0 and 2 pi, 2x, just by the properties of inequalities, 2x is between 0 and 4 pi. Right? Well, so let's find all the solutions from 0 to 4 pi of original tangent function. So from 0 to 4 pi, we get what? We get this point, which is 3 pi over 4. We get this point, which is 7 pi over 4. Now, so that's you back to 2 pi. Well, let's keep going. We have to go another circle, right? One circle is 2 pi. Another circle is 4 pi. So if I keep going past 2 pi, what is this? Yes. Because again, you've gone the full circle from here. It's plus 2 pi. So you get 7 pi over 4. And you go another, this plus 2 pi, you get 11 pi over 4. I'm sorry, 15. Yeah, this is 11. Sorry, yeah, this is 11. And you add 2 pi, this is 15. Yeah, that's better, right? Right, you go plus 2 pi plus 2 pi. So that means 2x equals 3 pi over 4, 7 pi over 4, 11 pi over 4, 15 pi over 4. And then you solve for x, you divide everything by 2. You get 3 pi over 8, 7 pi over 8, 11 pi over 8, 15 pi over 8. So you get the same solutions. Without thinking about the period, you just do all the solutions on 2 circles, and then you just solve for x. How's that? Which method made a little more sense? What? You just solve and then you use the period. Yeah. I mean, they're both equivalent. Yeah, because it doesn't matter whether you solve for single x and then you use the period of the function, or you do this. You kind of go backwards. Let's try another one with a double angle. I don't see anything with double angles. Well, this kind of has double angle. So here's an example. Cosine of 2x times sine x plus sine x equals 0. Okay. So now think algebra. This is kind of a messy equation. It has multiple functions and so forth. But there's a certain part that keeps repeating in that equation. So if this was just an algebra thing, what would the first thing you would do? If you have an equation, we have a sum that shares something and it equals 0, what's the nice thing you should do? Factor, right? So because if you convert this into product, if you pull out the sign, you'll get sine x times cosine 2x plus 1 equals 0, right? Just algebraically, if you factor sine x, well, now all of a sudden you have a product that equals 0, right? How do we solve equations? Again, we don't need to know what sines and cosines are to answer this question. How do we solve equations where you have a product that equals 0? Yeah, you set each factor to 0, then you solve them separately, right? This is your 0 product or factor property. So you take the first one, sine x equals 0, and you take the second one, cosine 2x plus 1 equals 0. Okay? So again, let's do the interval from 0 to 2 pi. Solutions on that. So the first one, that should be easy. When does sine equal 0? 0. Well, yeah, 0 pi. Right? The y value. When does y value equal 0 in the unit circle? At 0 and at pi. All think about the graph of the sine curve. And this is why we don't include 2 pi in our interval. Then we'll have to include 2 pi, and that's redundant. It's the same point. Okay. So that's nice. Now, many ways to solve cosine 2x plus 1 equals 0. Okay? Oh, actually, that one's almost silly. But so cosine of 2x has to equal -1. Okay? So again, we can do it the way we like the first method. When does cosine equals -1? At I think yes, right? At pi, right? So that means 2x has to equal pi, right? The insides has to equal pi, right? So that 2x has to equal pi, so what is x? Pi over 2. Now, what is the period of this function? What is the period of cosine of 2x? Oh, that's not good. So what's the period of cosine of 2x? Well, what's the period of cosine? So again, so what's the period of just cosine without any junk? Just the cosine. Yes, so the period of cosine is 2 pi. So what's the period of cosine of 2x? Now, pi. You divide by the constant, right? It increases the frequency, right? The graph shrinks. So the period here is pi. So to find another point, I'll just have to add pi to pi over 2. So then another point will be pi over 2 plus pi, which is 3 pi over 2. So here are my solutions. 0 pi, pi over 2, 3 pi over 2. Okay? So the solution set is 0, pi over 2, pi, 3 pi over 2. So we'll just... So that's just on the first circle. If the question was find all solutions, I mean, you realize that you just get increments of pi over 2. So just multiples of pi over 2, that's what you get. Because like 2 pi will still solve this, and so forth. But these are just solutions on the interval from 0 to 2 pi. You need to know the facts of what the period of sine and cosine is. Everything is 2 pi except for tangent, cotangent. Those are pi, right? So you need to know those facts. But did that make sense how we found the second solution? We could have done that other trick, find all solutions from 0 to 4 pi. So there will be pi and 3 pi. Then you divide them by 2. You get pi over 2 and 3 pi over 2. Questions on this? We had to use a little bit of old school algebra like factoring. Yeah. Like for example, well, I mean the first one I don't need to do anything else, right? But on the second one, let's say I convert the second one using the double angle formula. So I have 3 options. I probably shouldn't be using cosine squared minus sine squared because then it just gives me 2 different functions. I'll just use the one that just uses one function, okay? So which one is that? So let's say I'll use 2 cosine squared x minus 1, then it's plus 1 equals 0, right? Will this even work? I don't think I'm getting the... Well, this is... Well, there's it had plus 1, right? So this is cosine of 2x. So 1's cancel, so I'm down to 2 cosine squared x equals 0. 2 is irrelevant. So then it's just cosine squared x equals 0. If I take the square root, it's just cosine x equals 0. So when does cosine equal 0? It's pi over 2 and 3 pi over 2. So you get those 2 solutions. So yeah, I could have used that. If I convert it to sine, for whatever reason, if I wrote it as 1 minus 2 sine squared x plus 1 equals 0, I use the difference form of the double angle of cosine. So 1 plus 1 equals 2, right? And if I move 2 to the other side, that becomes negative 2. Divide by negative 2, you get sine squared x equals 1, right? Because you're dividing by negative 2. So that means sine x equals plus or minus 1, which is pi over 2 and 3 pi over 2. Right? Sine x equals 1 at pi over 2. Sine x equals negative 1 at 3 pi over 2. So you get the same solution. So it's really, yeah, sometimes it's beneficiary to use, especially for the cosines, because that's a simple formula. For tangents, yeah, just, you know, you don't need to use that formula. Because the tangent formula is messy. Yeah. What? Yeah, but see, we're going backwards. We're trying to take this tangent 2x and unsmash it. So questions so far. Now, we can totally use our calculator for this. So I have 1/2 cosine theta plus 1 equals some ugly thing. And let's say we'll go from 0 to 360. Okay. So again, start solving algebraically. So subtract 1 from both sides. So it gives you 1/2 cosine theta equals 0.2108. So solve for cosine. Then multiply by 2 to get cosine by itself. So cosine theta equals 0.4216. Right? So the first step was to isolate your trig function. Are we okay how we got to this point? So how can I find theta now? It won't tell me theta. I can find sine theta, but it won't tell me theta, right? Theta is the angle. Inverse. That's why we learned inverses. So when you end up with a number that's not familiar to us, like 1/2 and square roots of 2's, the numbers that we see in a unit circle, I can use the inverse. So theta equals the inverse of 0.4216, right? So I can use my calculator now. Since the question was find the solutions from 0 to 360, I have to make sure my calculator is in a degree mode, right? Well, I mean, that's different from what you're smiling about, but it's, right? So I'll just go 0.4216 inverse cosine, so yeah, whatever, 65 degrees. Will that be okay with you if I just rounded that dramatically? Or you want to go 65.06? I don't care. So 65. Usually, like, if you do this on your MyMathLab, they'll tell you round to like 4 decimal place or whatever. So 65 degrees, right? Are we done? I have to make sure I found all solutions. What? Yeah, from 0 to 360. So I'm still going to have to draw a unit circle. Okay? I'm going to use my understanding of where cosine is. So 65 degrees is something like that, right? So here's that point. Now cosine, is the cosine x or y value? X. So I need another point that has exact same x value. So where's that point? Same x value, right? So here's that other point. So that means if this is 65 degrees, so is that, by symmetry. So then the answer should be this angle, which is 360 take away 65. Do you agree with that? What? 295 you said? Yeah. Do you see what I'm doing? Just using the symmetry. I know the value that is 65 degrees. By symmetry, that's negative 65 degrees. Or 360 minus 65. So it's 360 minus 65, which is 295 degrees. So these are my two solutions. Is that okay? Because again, remember, the inverse cosine, remember how we restricted the domain for the cosine? Went from 0 to pi. So the inverse cosine will give us the answers from 0 to pi, from 0 to 180. Well, the question was find everything from 0 to 360. So just by giving me this is not sufficient. You have to go back and then play with the circles to find the second solution, or third or fourth. I don't know how many of them. But that's the idea. Is that okay? Well, usually you get 2 solutions for a normal function, okay, on the entire period. Because if you just think about the graph, okay, think about the graph of a cosine or any trig function on just first period. Any point is reached at most twice, right? Any value is reached twice, right? Any value is reached twice except for that one, right? Or 1, because we're not including that one. So 1 is only reached once and negative 1 is only reached once. But everything else will be reached twice on just on one period. Because if we change the period but keep the interval the same, maybe it's more. If this was 2 theta, so then the function will do this thing twice. So you'll get 4 solutions. Okay? Does that make sense? It's awesome. There's this mathematician, well, there was this mathematician. His name was, I don't remember his first name, but his last name was this. No, wait a second. So he's responsible for this, it's more of an applied math, he's responsible for what is called the theory of control, where you can in addition to your functions where you have normal variables, there's also a control variable, like, hey, I'm going to step on brakes. So you actually introduce a little control to your dynamic system, which is kind of, you're sending a thing to the moon, which is unmanned or whatever, or unwomaned, whatever it is. And at some point, you have to tell the thing to slap on the brake so it doesn't smash. So with all the variables, you have this extra. So it's a theory of optimal control or whatever. And there's this book. His original work is about, his whole book on that. And you flip through the book, and it's just full of this visualizations, and they're like circles with circles on the inside, just beautiful. Every page has a picture of all that theory and just blah. And all the formulas, and then pictures, pictures, pictures. And it's kind of, very important result, and you can model, landing things on the moon, using some of those formulas. And then you realize the guy was blind all his life, since he was like, yeah, he was, he went blind at like age of 7. He played like with a lamp that exploded in his face, lost his eyesight. This whole thing just blind. Yep. It is insane. And just this is what the funny thing, it was the most you read those higher math textbooks, they're pretty dry, just all formulas. And this was like one of the only ones that had pictures almost on every page. It's done by a blind man. Yeah. I had a professor once who was blind. He just lectured. He wrote on the board. He would use his one hand like this, and then he would be writing it, and he just kept tracking it like that. The man was blind, just lectured like that. Kind of cool. But yeah, that guy is.
I feel like having been able to see what a circle does, like before the age of 7, probably had something to do.
Well, maybe, yeah. He at least he knew what things looked like or whatever. He knew how to, write and all that. But yeah. And again, don't quote me on the whole 7 thing, but definitely young. Okay? Right. Anyways, little side note. So that makes sense. So when you start using calculators, still keep in mind that there might be more than just one solution, because the calculator will only tell you one solution. It cannot tell you more than one, because if it does, then inverse is no longer a function. It cannot tell you 2 solutions, because the functions don't do that. Well, not really. This is just, and again, like there'll be rules like with sines. If this was a sine problem, then another solution is here. So you'll go 180 minus 65. For the cosines, it's 360 minus 65. But don't try to memorize that. Just draw a circle every time, and it will tell you which way to subtract. Okay? That's easier. It's a good habit. All right, how we doing on time? We're doing good on time. Well, let's try this one. Sine x plus 3 equals 2.0816. So what do you want to do first? Subtract 3. You want to isolate your trig function. So it's sine x equals negative, what is it, 0.9184-ish? Is that right? And let's do again from 0 to 360. So at this point, I have to use the inverse sign, right? Because I have no idea what this number is. Number is between -1 and 1, so I know there will be a solution. Now, on which interval will my solution land? What is the range of the inverse sign? The range. So how did we restrict the sign domain to make that? No, that's the domain. Yeah, so it's from pi over 2 to pi over 2, right? So the answer that we'll get will be in this region. And since it's negative, it will be on this side. And if it's -1, it will be really close to. That's what we'll get for our answer. We'll get a negative degree measure. Okay? And then we'll have to find the other one, which will be here. Right? And I'll have to get really creative. But anyway, so let's just do that first measure. So I need to go 0.9184 negative, and then inverse sine. Bam. So negative 66.7. Right? So x equals negative 66.7. Is this one of my solutions? Well, but it says find all solutions from 0 to 360. Negative 66.7 is not from 0 to 360. So I actually have to think of this point like that, right? So I have to subtract that number from 360, which is equivalent to 360 minus 66.7. So actually that value would be, 293.3. How is that? Right? So I cannot have a solution negative 66 when the question is find solutions from 0 to 360. It's outside that interval. So you have to convert it to that interval by adding 360 to it. Okay, so we figured that one out. How about this point? How do we find the value for that? Oh, wow. Well, probably not, because I'll get a negative solution. But if you do the other way around, it might work, but you're making it a little too complex, I think. Just think about this. This is 66.7, right? So is this. This is 66.7. So you can go 180 plus 66.7, right? Or you can go 270 minus whatever's left out of 90 there. So the other solution would be 180 plus 66.7, which is 246.7. So here are your two solutions on the interval from 0 to 360. How's that? Is this okay? All right. Let's keep going. So now I'm going to give you something that's just beautiful. 10 sine squared x minus 12 sine x minus 7 equals 0. And again, let's just go from 0 through 360. What does this remind you of?
No, that's not what I meant. Like the
Quadratic.
Yeah, it's a quadratic equation. You have something that's squared, something that's not squared, and a constant. It is of this form. It looks like ax squared plus bx plus c equals 0, right? So we can solve it like a quadratic equation, right? We know that a general solution to, you're going to try to factor first. I don't think that'll work. General solution to a quadratic equation is the whole negative b plus or minus the square root of b squared minus 4ac over 2a. Right? That's the quadratic formula. So I'll just ignore the fact that I have signs instead of x's. I'll just say a is 10, b is negative 12, and c is negative 7. So that means equivalently, sine x will equal to negative b, which is 12, plus or minus the square root of b squared, which is 144, minus 4ac, so it's minus 4 times 10 times negative 7, all over 2a. So I'm solving for sine x instead of x. Is that okay? Then I'll solve for sine by using inverses or whatever, but I'm just treating it as a quadratic, ignoring, I mean, it doesn't matter that it's a sine right now. So anyway, so play a little further, so it's 12 plus or minus, what is this? This is 47 to 80. 2 minuses give you a plus, so it's 144 plus 280, so it's 424. Is that right? Yeah, okay. Over 20. Okay. I'm sure I can reduce it and simplify it or whatever. Like I'm sure I can pull out a 4 out of the square root, reduce this fraction. But I'm just going to end up plugging in the calculator anyways, because I'll have to figure out the values here. So I get sine x equals. So I'm just going to plug this in the calculator. So I'm going to do the plus and then the minus separately. So 424 square root of that plus 12, that's my numerator, divided by 20, so 1.63. And the other one, I'll do the same thing with the minus. 424 square root of that, make it minus, add 12, divide by 20, so negative 0.43. Is that okay? So now I'm going to start using some inverse sine functions. Does the first equation have a solution? No, because that's bigger than 1. Sine is never bigger than 1. Sine is between negative 1 and 1. So this one has no solutions. Even if you plug this in the calculator will tell you that it has no solutions. But on this one, I'll have to use the inverse, so it's x equals the inverse sine of negative 0.43. So I'll end up in the fourth quadrant, because it's a sine, it's negative. So the solution will be in the fourth quadrant. So 0.43 negative inverse sine, so negative 25.5. I mean, I'm really, I don't know, free with my roundings here, but so negative 25.5. I'm ignoring how many decimals we're carrying, so negative 25.5, right? So it's somewhere here, right? Negative 25.5. Where's the other solution? In the third, because it's a sine, so I'm looking for the same y value, right? So sine is the same y value. Now, since this is 25.5, negative, so I need this angle right here. So it's 360 minus 25.5, right? I cannot have a solution negative 25.5 because we're from 0 to 360. So x has to be, I have to put that. So x equals negative 25.5 plus 360, which is 324.5. No, 34, right? Degrees. What about the other one? Yeah, 180 plus 25.5, right? So it's 180 plus 25.5, so that's 205.5. So these are my two solutions. Okay? And if I take 324.5 degrees and I plug it into this equation, it will virtually work out. It won't give me the exact, because I've been rounding a lot. But if I just do this, if I plug, so what was that? 324.334, okay. 334.5, right? Degrees. And I'll take sine of that, and then I'll square that, then I times it by 10, and then I'll store it in my memory. And then I'll do 334.5 sine of that times -12 equals that. And then I'll add that to my memory, right? So the result in there should be, my memory should be pretty close to 7, because -7 equals 0. So if I do memory recall, I should get something really close to 7. So yeah, that's my rounding error. I was rounding a lot. So yeah, it works when I plug it back into the original, which you don't really have to do, but okay. So you'll be faced with a lot of this, with a lot of quadratics. That you solve them just like a regular quadratic, only instead of solving for x, you solve for sine or cosine, and then you use your knowledge of trig or whatever. So not everything can be solved this pretty. Sometimes you have to just use a graphing calculator or something like that. Now, sometimes you see problems like this. Here's a fun one. Sine x plus cosine x equals 1. Okay. Now, not the squares, just sine plus cosine equals 1. So it's not always true. I need to find the values of x where that's true. So one thing you might have noticed so far, it's always easier when my equation is in terms of a single function. It's either all in terms of sine, or it's all in terms of cosine, or it's all in terms of tangent. At least I can factor and separate. Not the case here. There's nothing I can do algebraically to make it all in terms of sine or all in terms of cosine, right? Because those are not squares. If they were squares, then life would be really good. Yeah, but then I'll get sine minus cosine on the other side, so I'll still have the singles. But I can square both sides, right? That's borderline legal. If I just do this, then see what happens. What's on the left? It is sine squared x plus 2 sine x cosine x, right? Plus cosine squared x still equals 1. So I squared the left, I squared the right. Now I have sine squared plus cosine squared on the left. What does that equal to? Right? We have sine squared plus cosine squared. That equals 1 plus 2 sine x cosine x equals 1. So 1's going to cancel, right? Minus 1 minus 1. So we have 2 sine x cosine x equals 0. Is that okay? So there are two ways I can solve this equation. Let's wait till you catch up. One way I can look at this, it's a product. It's a product that equals 0, so I'll set sine equals 0, cosine equals 0, solve both of those separately, right? Because it's a product. Or I can say 2 sine x cosine x is the double angle formula. It's a sine of 2x. And I can do it. I can go from there. Does that make sense? So options, but let's just, I think the easy one, just do them separately. The 2 doesn't matter in this case. So when the sine equals 0, let 0 in pi, right? And when does cosine equals 0? that okay? I mean, are you okay how we got those? If I'd gone the other route, if I said the left hand side is just sine of 2x, that's equals 0. So that's kind of like doing the double angle ones, right? So the solutions from 0 to 4 pi would be 0 pi, 2 pi, 3 pi. Then you divide all by 2, you get 0 pi over 2 pi, 3 pi over 2. So you still get the same solutions, right? 2x has to be between 4 pi and 0, so the 2x would be 0 pi, 2 pi, and 3 pi. Then you divide everything by 2, x equals 0, pi over 2 pi, and 3 pi over 2. You still get the same solution. Okay? Now let me ask you this question. When solving equations, and then think about the algebra class, were there types of equations where you had to square both sides? You remember doing something like that? Just here's an equation, you squared both sides. When did you use that technique, when you square both sides in algebra? What has to be a part of the equation so you would feel like, I should square both sides? Square root, right? When you had equations that had square roots, you would isolate the square root, then you would square both sides to get rid of the square root, then you would solve the equation. And then you had to do this one last thing in the end. When squaring both sides, when solving equations that involve radicals in algebra, no. See, when you square root both sides, you plus 1. When you square both sides and you find your solutions, you have to do something with that solution. What does that mean? When solving equations that involve radicals, when square both sides, or something might happen. Yeah, you want to check your answers because you might get the so-called extraneous solutions. Because when you square both sides, it totally ignores the signs. Right? Because then, if my left comes out to be -1, which is not true for this equation, but if I square both sides, it works out. So I have to check all of my solutions. So let's check. If I take 0 and I plug back into my original equation, sine of 0 equals 0, cosine of 0 equals 1, 0 plus 1 equals 1. Happy, right? So 0 works. How about pi over 2? Sine of pi over 2 equals 1, cosine of pi over 2 equals 0, 1 plus 0 equals 1. Good, right? Pi. Sine of pi equals 0, cosine of pi equals -1. 0 plus -1 does not equal 1. Right? So pi does not work. It's one of those extraneous solutions. Because, hey, your left side came out to be -1, your right side came out to be 1, but we squared both sides, so that made them equal. So that's why pi showed up as a solution. It equals when you square this, but the original equation doesn't have squares, so pi does not work. 3 pi over 2, sine of 3 pi over 2 is -1. Cosine of 3 pi over 2 is 0. -1 plus 0 does not equal 1. So these two, which ones were those? 3 pi over 2 and pi, right? Those two were extraneous solutions. So the only solutions are 0 and pi over 2. So it's the same reason why we had to do this when solving equations with square roots. You have to check your solutions because you might get that because the sign becomes irrelevant when you square both sides. So you have to make sure it still works. If I look at this problem graphically, if I grab this too, because sometimes there's nothing else you can do but to solve them graphically. So one function is sine of x, so that's the left hand side, plus cosine of x, and the other function is just 1, and I don't need the parabola, right? So now think about the interval from 0 to 2 pi. So where is 2 pi? So that's that interval, right? This is the 2 pi, 6 point something. So see, it only has 2 solutions here and there. That's where they intersect. But our solution gave us those 2 as well when they both equal -1. But I don't want -1, I just want +1. Okay? Or another way to think about this, if I subtract 1, then I'm just looking for the x-intercepts. So those are 0, and I'm pretty sure that's pi over 2. That thing right there. Okay, and that's 2 pi. Does that make sense? Okay, good. All right, so that's our